Welcome to this NPTEL lectures on robotics, basic and advanced concepts. In the last lecture, I had introduced the various topics in robotics, basically a little bit of history, a little bit of how they are classified, and then I had shown you some videos of some well-known robots. In this lecture, we look at the main elements of a robot. So a robot is a very sophisticated and expensive equipment even now. Okay. So the components making up a robot undergoes constant improvement and advancement, and it is very hard to keep up. So initially the motors had some specification. Now they are much better. Similarly, there were some sensors which were used earlier. Now they are much better sensors. So it is sort of hard to keep up with all the various mechanical, electronic, and computer or sensing components which go into making up of a robot. Okay. The main components are mechanical components, actuators, transmission devices, sensors, electronics, and computers. Okay, these are some of the key components which go into making a robot. The main mechanical components are links and joints. Okay, so link is basically the member, okay, which carries the load, which moves, okay, which positions something or other at the end of the link. The links should be strong and lightweight. Okay, so most of the time they are very lightweight because they are made using die cast sections, okay, made of aluminum quite often. The joints should be friction and backlash free to the extent possible. Okay, because if you have friction and backlash, the joints will introduce errors, okay, which sometimes the controller cannot overcome. The actuators are typically electric, pneumatic, or hydraulic. Okay, and transmission devices are needed to transfer the motion from the actuators to the joint, okay, in a proper manner. So we will look at all these components. We look at links and joints, we look at actuators, we look at transmission devices, and then we will also look at sensors. Okay, the sensors enable a robot to possess touch and feel, sense motion and force, and to see and learn. Okay, sensors are required for feedback control. These are sometimes called as internal sensors. There are also external sensors which you can sense touch and force, you can measure distances, and you can have cameras which can see the environment. Okay, there are also some specialized sensors for welding, painting, assembly, and other industrial operations. Okay, so we need to make sure that the weld bead is correct height, and we can change some parameters automatically, or you can see that the welding is happening at the right place. So those are very specialized sensors. The computers and software which go into a robot are often more expensive than the hardware. Okay. We have one or more processors to control the motion of the actuators. We sometimes have processors for signal processing and sensing. We also have processors for user interface, data logging, communication, and other activities. So typically in a robot, you have a lot of computing power, okay? And there is a lot of software which have been ported onto these computers to do a variety of tasks, okay? We also have offline programming system with user-friendly GUI to train operator, verify motion, and reduce downtime of a robot. So basically, since a robot is so expensive, we don't want it to be lying idle, and we don't want such a robot to be used for training. Okay, we would like to train the operator in a virtual environment, that is what is called as the offline programming system. So we have a CAD model of the environment, we have a CAD model of the robot, and we can make this robot move, okay, and train the operator in this virtual environment. Let's continue. As I said, we'll look at joints, links, actuators, transmission devices, and sensors in this lecture. So what is a joint? Joint is nothing but a element which connects two or more links. Okay, so basically what does a joint do? It imposes constraint on the link it connects. So if you have two rigid bodies in 3D space, you have six, each of them with 6 degrees of freedom. So you have 12 degrees of freedom. If you now connect these two rigid bodies using a hinge joint, okay, hinge joint is nothing but one which allows rotation or relative rotation between the two connected rigid bodies. So in that case, then you have 6 plus 1 degree of freedom. So basically what has the hinge joint done? It has removed 5 degrees of freedom. So it has imposed 5 constraints. Okay, so hinge joint allows 1 relative degree of freedom. So we will look at these constraints and more detail in the lecture on kinematics of serial robots. Okay, and before that, in the second week, when we discuss mathematical representation of links and joints in more detail. The degree of freedom of a joint in 3D space is 6 minus m, where m is the number of constraints imposed. So, for example, a spherical joint or a ball and socket joint will impose 3 constraints, and the degree of freedom is 6 minus 3, which is 3, which very easily known or can be very easily seen. In a serial robot, all the joints are actuated, okay, and most of the time 1 degree of freedom joints are used. Okay, in a parallel robot or in a hybrid robot, some joints are not actuated. They are called passive joints, and those passive joints can be multi-degree of freedom joints. So, for example, in the Stuart platform, which I showed you earlier in the last lecture, there were these spherical joints, but they were not actuated. There was a hook joint, and then that was also not actuated. The only actuated joint was the sliding joint. These are some of the typical joints which are in use in robotics. Screw joint, not so common, but sometimes it is used. So basically, you have one member which is the shaded and one member which is the white portion. The white portion can rotate and translate about the screw axis, okay, just like a normal screw. It is a 1 degree of freedom joint simply because the rotation and the translation are related by the pitch of the screw. You also have rotary joint. It is 1 degree of freedom joint. Again, we have two members, just like a hinge joint, and the second member can rotate with respect to the first member. So this is theta is the typical variable which is used to denote a revolute joint. We also have prismatic joints where one member can slide up and down this other member. Okay, and the variable which is used to denote this sliding motion is D typically. We have a 2 degree of freedom cylindric joint, which are sometimes seen in closed loop mechanisms, where this theta rotation and this sliding D are not related. There is no pitch. Okay, they are independent. As I said, we can also have a spherical joint which has 3 degrees of freedom. Spherical joint is nothing but a ball and socket joint. And this is another theoretical joint which is called as a planar joint. So basically you have two planes and there is relative 3 degrees of freedom between these two planes. Okay, the second object here can slide in the x and y direction and also rotate with respect to the other object. And we have a hook joint or a universal joint where you can have 2 degrees of freedom about two independent axes. So these are some of the common joints which are used in robots and in some closed loop mechanisms and parallel manipulators. Let's continue. A link is a rigid body in 3D space. Okay, as far as we are concerned in kinematics, dynamics, and control, okay, most of the time in control, it is a rigid body in 3D space. Okay, most robots are rigidly built. We will not look at the deformation or the deflection of a link. If you are interested in the space shuttle arm, then we need to worry about the deflection. Then the link is no longer rigid. Okay, and we have to introduce this deformation and deflection of the members of the robot. A rigid body in 3D space has 6 degrees of freedom. So it can rotate about 3 axes. So there are 3 rotation degrees of freedom and there are 3 translation degrees of freedom. So it requires 6 parameters. Okay, so a link of a robot would require 6 parameters in general. However, if the links are connected by rotary and prismatic joint, it is possible to use 4 parameters only to describe the relative motion of one link with respect to another link. Okay, or describe one link with respect to another link. So these are known as the Dennewitt-Hartenberg parameters. Okay, and they were invented by these 2 researchers, Dennewitt and Hartenberg, in 1955. So as you can see, this is very useful because almost for the last 65 years they have survived. If something is not useful, then it would have died long time back. And the basic reason why it is useful is I don't want to carry around 6 parameters. Okay, if I can get away with 4, it is 2/3 less. So, and in a robot you will have many rigid bodies. So you can see that if you have 6 rigid bodies connected by joints, we don't need to worry about 6 into 6, 36 parameters. We can get away with 24. Okay, so these 4 parameters are possible since lines are related to rotary and prismatic joints are used. Okay, so we will look at in the kinematics portion of this robotics course what are the DH parameters and how to find the DH parameters. Okay, what are the exact definitions of each of these 4 DH parameters. For multi-degree of freedom joints, if you have a multi-degree of freedom joints and you want to use these DH parameters, then you have to replace this multi-degree of freedom joints with 3 or more or more than 1 degree of freedom joints. Okay, so for example, if you have a spherical joint with 3 degrees of freedom, you can use 3 equivalent rotary joints. Okay, so this is a good thing to do. So this is a very nice approach. It has a lot of advantages. We can get away with 4 parameters. Unfortunately, there are several DH conventions possible. Okay, and many textbooks will have one way to describe the DH parameters, and some other textbooks will have another way to describe these DH parameters. Okay, it turns out that that is what happens when you go from 6 to 4. You have several possibilities. We will be using the DH convention, which is there in my book, or it is actually borrowed from the book by Craig, a very well-known book, okay, on robotics. So let's look at the robot. What do we really mean by, how do we really describe? This is a very brief introduction. We will look at all these things in much more detail in the second week. So in this Puma robot, we have 6 joints. So one rotary joint is here, where my cursor is. One rotary joint is perpendicular to that vertical joint. There is a third rotary joint here. So most of the time we'll see Z1, Z2 or Zi denoting the joint axis. Okay, and then there are these 3 rotary joints which are intersecting at this point. This is also sometimes called as the wrist point. So we have Z4, Z5, Z6 which are intersecting at the same place. And as you will see in more detail later, the DH parameters are these distances A2, D3, A3, D4, okay, and so on. Okay, these are link lengths and link offsets, and you will also have some twist angles. So the angle between joint 1 and joint 2 is one such parameter. In this case, it has been built with 90 degrees. Okay, built so that they are at 90 degrees to each other. So we will have all these 4 parameters, which we will describe in more detail next week. Interesting thing in this design is that the last 3 joint axes intersect at one point. Okay, and this gives a lot of advantages in the modeling and analysis of this robot, especially in kinematic analysis. Okay, so as I said, there are these 4 DH parameters. Most of the time, these 4 DH parameters are given in the form of a table. Okay, so in this table, what you have is I, which is the link numbers. So these are 1, 2, 3, 4, 5, and 6. The Puma has 6 links. And along the row, you have this alpha I minus 1, AI minus 1, DI, and theta I. So these are the 4 DH parameters for each link. So for example, for the third link, alpha I minus 1 is 0, AI minus 1 is some quantity A2, it's a number, it's a distance, DI is D3, another distance, and theta I, which is the rotation of the third link. Okay, it's a joint variable. So in this Puma, all the joint variables are rotary joint variables, which are represented by theta. Okay, I discussed this, I told you earlier. So we have theta 1 through theta 6 as the 6 joint variables. As you can see in this DH table, many of the alphas are very simple. It's either 0 or plus minus pi by 2. Okay, and that is how most robots are designed and built. Okay, it could have been 30 degrees or 22.5 degrees, but normally as a designer, we pick these nice simple parameters. Okay, when you buy a robot, you will get a table like this for any robot, and basically they will give you the DH table for that robot. So if you have a 6 degree of freedom robot, you will get a table with 6 rows. If you have 4 degrees of freedom robot, you will get a DH table with 4 rows. Okay, this is supplied by the manufacturer, who in turn has obtained it from the designer. Let's continue. The actuators are required in a robot to move the joints, to provide power, and to do work. Okay. In serial robot, actuators must be of low weight. Okay, why? Because the actuators of the faraway links, the distal links, need to be moved by the actuators near to the base. Okay, so in the case of the Puma robot, the actuator which is driving this fourth joint, okay, must be moved by the first joint. So if you have a very heavy actuator sitting on this fourth joint, the first joint will have to do a lot of work. Okay, it has to put in a lot of effort. It needs to be very powerful. So we need actuators which are lightweight and of high power. Okay, the actuators, the distal links need to be moved by actuators near to the base. In the parallel robot, often actuators are at the base, so we don't really have to worry too much about moving another actuator. The actuator drive a joint through a transmission device, and we'll come to that. Okay, so the motor most often is not directly connected to the rotary joint. There'll be some in-between device which is called as a transmission. And there are 3 main types of actuators: hydraulic, pneumatic, and electric motors. So these are some pictures of typical actuators. So on the top left where my cursor is, this is a pneumatic actuator. So basically in a pneumatic actuator, we have some reservoir where compressed air is kept. Then you have some kind of a valve. Then you can have some kind of a regulator and a solenoid. And then this lets in the air into this actuator. So when air is let in, this end will go in and out. Okay, sometimes you have inlet at 2 places, one to send it in one direction and one to send it in the other direction. Okay, the hydraulic actuator is something very similar, except instead of air, you have compressed oil. Okay, so hydraulic actuators can transmit much more force. Can transmit much more power. Okay, because air is light and it is compressible, whereas oil or water is incompressible. We can also have a DC motor. Okay, so this is a nice picture of a DC motor showing all the parts. So basically what do we have? We have a rotor, which is not really seen here, which is most of the time a permanent magnet. And then on top of that, we have the stator, which is coils. Okay, so we send current through these coils, and due to Faraday's law, the rotor, which is permanent magnet, will start rotating. Okay, if the direction of the currents has changed. We also have a device which is called as an encoder. Okay, which will measure the rotation of this rotor shaft, because in control we need to know how much is the motor rotating. Finally, we also need to somehow reduce the speed of this rotor shaft. Okay, typically a motor will rotate very fast, maybe 2000 rpm. You cannot connect the shaft of the motor directly to the joint. So there is, most of the time, there is some kind of a transmission device. In this case, what is shown is a gearbox, which will reduce the speed of the output shaft. So these electric motors or electromagnetic actuators are widely used in robots. They are readily available in wide variety of shapes, sizes, power, and torque range. They can be very easily mounted or connected to the transmission elements such as gears, belts, and timing chains. Okay, they are also amenable to modern day digital control. Okay, so they have an encoder which measures the rotation, and we'll see later that this measured rotation of the shaft can be used to control the rotation of the motor shaft or the speed of the motor shaft. Okay, there are three main types of electric actuators which are in use. One is called stepper motors, one is permanent magnet DC servo motor, and there is something called brushless motors. Okay, in a brushless motor, the currents are not switched in the direction we want, okay, by means of brushes. It is done electronically. The stepper motor is normally used in small robots with small payload and low speeds. Okay, stepper motors cannot provide too much torque or cannot operate at very high speeds. Stepper motors are typically permanent magnet, hybrid, or variable reluctance type. Okay, so these are some terms which are common in stepper motor literature. Okay. A stepper motor is typically actuated by a sequence of pulses. Okay, so for a single pulse, if I give a single square wave, a single pulse, then the rotor will rotate by one step. Okay, and how much does it rotate? So the steps are such that the rotor and stator will become aligned at the end of the step. So the typical step sizes in stepper motors are 1.8 degrees or 0.9 degrees. So every time you give a step, it rotates by 1.8 degrees or 0.9 degrees. Okay, and the speed and direction of this stepper motor output shaft can be controlled by the frequency of these pulses. Okay, so if you want to rotate very fast, you give these pulses at a higher frequency. One of the advantages of a stepper motor is that it can be used in open loop. Okay, why? Because there is no cumulative error. The maximum error in a stepper motor is typically one step. So it will be maximum of 1.8 degrees or 0.9 degrees depending on the step size in the stepper motor. A stepper motor can also be used in micro stepping mode. Okay, so basically what is micro stepping? We don't want 1.8 degrees, but let's say we want 1/10 of this, okay, 0.18 degrees. So this can be achieved, and for that we need closed loop feedback control. Okay, and when you do micro stepping, there is a loss of torque in the stepper motor. Most of the time, stepper motors cannot provide large torques, and in micro stepping, the output torque is even smaller. This is a typical picture of a stepper motor. Okay, so there is a rotor which contains all these teeth. Then there is a casing, motor casing, and then there are the stators with coils. Okay, so schematically what is shown here is the rotor with number of teeth, okay, which are magnets, and the stator which are coils. So basically what happens is if electromagnet 1 is activated, the rotor rotates such that the nearest teeth line up. Okay, if electromagnet 1 is activated or deactivated and 2 is activated, okay, then the rotor rotates such again the nearest teeth line up. Okay, and this rotation is by a step, which is typically 1.8 or 0.9 degrees. If 2 is deactivated and 3 is turned on, again it will rotate by one step, again till the teeth line up. Okay, and so on. So it keeps on activating and deactivating, and at each time there is a step which is done. Okay, so a permanent magnet stepper motor is similar to this variable reluctance stepper motor. This is the variable reluctance stepper motor which is shown, except the rotor is radially magnetized. Okay, we instead of these teeth or magnetized teeth, we have this radial magnetization. And we can also have hybrid stepper motors, which basically combines the best features of variable reluctance stepper motors and permanent magnet stepper motors. Okay, so we can also have DC or AC servo motors. A rotor is a permanent magnet again, and the stator is a coil. The permanent magnets are typically made with rare earth materials. Okay, so there are these samarium, cobalt, neodymium, and various other rare earth materials which can be used to make very strong magnets. Okay, which can give very powerful magnetic fields, and hence we will get high torques. Commutation is done using brushes or in brushless motor using Hall effect sensor and electronics. Okay, as I said, if you have brushes, then this is the standard DC motor. Okay, you change the direction of the current because the brushes work in that way. You can also do this commutation using this Hall effect sensor and electronics. These are called brushless motors. A DC actuator, okay, or DC servo motor actuators are widely available in large shapes, sizes, power, and torque range. And these are very, very reasonable nowadays. Okay, it's also easy to control because most of them come with a optical encoder, or we can fix an optical encoder at one end. You can also attach a tacho generator which mounted in line with the motor shaft. Okay, and then we can measure both the rotation as well as the velocity, the speed of this motor. Okay, the brushless AC and DC servo motors have very low friction because there is almost nothing in contact. They are also very low maintenance, they are low cost and robust. Okay, so most of the time nowadays the trend is to use these brushless DC motors, also sometimes called as BLDC motors. So here are some of the pictures of some of the well-known DC motors, out of which this is an interesting motor. These are called small RC servo motors. Okay, these are toy motors. These were originally made for remote control toys, RC. That's why the word RC comes from. And they are easily available in internet. These are some very well-known companies like Pitman. Then there is also some other companies which make these DC servo motors, DC brushless motors. This is another interesting DC motor. Okay, this is what is used in electric bikes and cars. So most of the time we have seen that the rotor is inside and the stator is outside. So we provide current to the stator and the inside rotor rotates. In a bike, electric bike, we invert it. So the stator is inside and the rotor is outside. So we provide current to the stator, and the rotor is basically on which a wheel is mounted. So as you can see, this looks like a hub. Okay, and we can mount a wheel on top of this. And when you provide current to the stator now, the rotor which is outside will rotate. Okay, and they come with variety of ranges, which you can get some 48 volts, 24 volts, 60 volts, various kinds of DC voltage which needs to be applied, and then the wheel will rotate. And they can be directly used in electric bikes and even nowadays in cars. This is also sometimes called as a hub motor. Why? It will directly fit into the hub of your bike. How is a DC servo motor normally driven? Basically what we have is, we have what is called as a PWM circuit. Okay, so what is a PWM circuit? We provide a pulse of between 0 and 12 volts, and we modify the width of this pulse. Okay, so for example, if it is on, for T1 and it is off for T2, we will get some average voltage. Okay, if it is on for full length of time, then you will get 12 volts which you are applying to the terminals of the motor. So this quantity T1 divided by T1 plus T2 is called the duty ratio. And by changing this duty ratio, we can give a different average voltage to the motor. Okay, and this step is done at a very high frequency. So the advantage of this is that we are only not changing the actual voltage we are applying, but we are changing the duty cycle electronically. So that is why this is called as pulse width modulation. Okay. The way to drive a DC motor is basically using something called as a H bridge. Okay, so we have transistors and we have an input which is forward and reverse, two inputs, and then we have this arrangement which looks like a bridge, H bridge. Okay, so if the input is 0 and this is also 0, the motor will be off. If the input A is 1 and the input B is 0, then the motor will rotate in the forward direction. The current will go such that the motor will rotate in one direction. If you switch the order of the input and make A as 0 and B as 1, then you go in the reverse direction and you cannot have both inputs. So basically what you are doing is by switching input A and B to 0 and 1, again using digital control. The whole idea is we want to do everything digitally. Then we can make the motor go forward, backward, or be off. Okay, so these two things enable a DC motor to be controlled electronically. We can control the speed by modulating the width of the pulse, and we can change the direction by switching between the two inputs. Okay. Let's continue. Let's look at transmissions which are used in robots. So the purpose of a transmission is to transfer power from the source to the load. Okay. It is also to transfer power at an appropriate speed. Okay, that is important. Let's take an example. Typical rated speed of a DC motor is between 1800 and 3600 RPM. Okay, so for the sake of argument, quick calculation, let's assume that the rated speed of a DC motor is 3600 RPM, which is nothing but 60 rotations per second, which is roughly equal to 360 radians per second. Okay? I'm assuming pi is 3. For a typical 1 meter link, if you connect this motor to a 1 meter long link, the tip speed will be omega times r. Okay, r is 1, so this is 360 radians, we'll get 360 meters per second. This is really, really high. It is in fact greater than the speed of sound. Okay, so hence we require a very large speed reduction. And that is the reason, one of the purpose of the transmission is to transfer power at the appropriate speed. Okay, what is the typical appropriate speed? So instead of 60 RPS, we probably need 60 RPM. Okay, 1/60th of this. Even then, it is like 6 meters per second, which is not a good idea. We even need more speed reductions. Transmissions can, if needed, also convert rotary to linear motion. So sometimes you have a motor, but I want to implement a prismatic joint, a sliding joint. That can be done by using what are called as ball screws, where the nut of the screw moves up and down when you rotate the inside. Okay. Transmission also transfers motion to different joints and to different directions. Okay, so I can have one motor in one place and I can, using belts and chain or some other kind of transmission, transfer the motion to some other joint at some faraway place. Not very far away, at a distant place. The transmission in robots are decided based on the motion, load, and power requirements. okay, and by the placement of the actuators relative to the joint. What are some of the desired properties? It should be stiff, it should be low weight, it should be backlash free and efficient. Direct drive motors with motors directly connected to the joint are sometimes used. Okay, it has the advantage of low friction and low backlash. Most of the time, whenever you have a transmission, you are introducing friction and backlash, but these are very expensive. Typical transmissions are gearboxes of various kinds: spur gears, worm wheel, planetary gears. We can also have belt and chain drives. We can have harmonic drives for large speed reductions. We can have ball screw and rack and pinion drives to transform rotary to linear motion. And sometimes we also have kinematic linkages. So we can have a 4-bar linkage to transmit motion from a motor to some jaw of a gripper. Okay, so this is an example of a harmonic drive. Basically, in a harmonic drive, we have two flexible members which are called splines, and because of the flexibility, you can give very large speed reduction. You can have very sophisticated gear reduction mechanisms. Okay, this looks like a cutout view of a gear reduction mechanism with lots of ball bearings and some gears and various other things. This is a picture of a ball screw. So basically you have this screw and this is the nut, but in between the nut and the screw there are these balls. And the advantage of these balls is that it reduces frictions dramatically. And as I said a few minutes back, that you can have a 4-bar mechanism to move the jaws of a gripper. So when I rotate this motor, and if you have this 4-bar mechanism, 1 link, 2 link, this is and so on, and if you move this, these jaws can move parallel to each other, which is of advantage. Okay, we want to grip an object, we want the jaws to move parallel to each other. Next, we come to elements of a robot, which are sensors. Okay, a robot without sensor is like a human being without eyes, ears, and sense of touch, etc. Okay, a sensorless robots requires costly time and consuming programming. It can only perform in the playback mode if you don't have sensors. It cannot adjust to the change in environment, tooling, and workpiece. Okay, if the tooling and workpiece has changed, we cannot account for it in the robot. Sensor constitute the perceptual system of a robot. Okay, they are designed to make inference about the physical environment. They are designed to navigate and localize the robot by itself. And they respond more flexibility to events occurring in the environment. Okay, so if somebody comes in front of this mobile robot, it will stop. Okay, when the person has moved away, it can again resume its path. Sensors are designed to enable learning, thereby endowing robots with intelligence. Sensors allow less accurate modeling and control. We'll see later on when we look at control. And sensors enable robots to perform complex and increased variety of tasks reliably, thereby reducing cost. Okay, let us continue. There are two main categories of sensors in robots. These are called as internal and external sensors. The internal sensors measure variables for control. Okay, so we need to measure the joint position. We can use what are called as incremental and absolute encoders. We need to measure the joint velocity. This is measured using something called as a tachometer. We often need to measure the joint torques and the force which the robot is applying to the environment. There is something called as the force torque sensor, which you can mount at the wrist or the end effector. So position, velocity, and force are often used to control the robot, okay, to achieve the desired task or to apply the desired force. We also have sensors which are called as external sensors. These are basically for proximity. We want to detect something very close to the robot. You also want to detect slip. So if the robot is gripping some object, how do we know that it is gripping properly and that it is not slipping? We also need to measure distance of the robot from an obstacle or from some other object which we want to go towards or we want to avoid. And there is this thing called cameras and vision sensor, which are very powerful external sensors. A camera can be used for a wide variety of tasks. Let's look at optical encoders. An optical encoder consists of the following items. So basically there is an LED, one or more LED, and then there are these photodiodes. There is a transparent disc, and on it we deposit by etching or photo depositing patterns. Okay, most of the time these patterns will be stripes, dark stripes. Okay, you can have some other pattern also, especially in absolute encoders. So now let's connect this disk to the motor shaft. So when this motor shaft is rotating, the light from the LED will be alternately obstructed by these dark stripes, and at the photodiode we'll get a signal. Okay, so that is the signal that we measure. Okay, so we count the number of pulses at the photodiode, and as we will see a little later, from that we can find the number of rotation, the amount of rotation, and even the direction. Okay, so this is one of the most important and widely used internal sensor. Okay, it can measure the rotation of the motor shaft. As I said, it consists of an etched encoding disc with photodiodes and LEDs. The disc can be made of glass, plastic, or even metal. As the disc rotates, light is alternately allowed to reach the photodiode, resulting in a digital output similar to a square wave. Okay, so this is what it looks like. So there are typically in an encoder 3 such outputs. One is called A, so you can see one square wave. Another one is called B, which is slightly shifted. Okay, A and B are more or less similar, but it is shifted by some distance, okay, in time. And then there is something called I. This is also called as the index pulse. Okay, so channel A, B, and I are typically available. A and B are phase shifted by 90 degrees, and I is called the index pulse, and this is obtained when the disc completes one full rotation. Okay, so every time you get an index pulse, you know that the disc has rotated fully by 360 degrees. So as you can see from this A and this signals A and B, these pulses, okay, are counted in a microprocessor. Okay, so depending on A and B, okay, the number of pulses tells you how much it has rotated and which one is leading. If A is leading B, then it is rotating in one direction, and if B is leading A, then it's rotating in the opposite direction. Okay, so this is an encoder which is sometimes called incremental encoder. We can also have encoders which measures the absolute rotation. Okay, we can also use these signals to estimate velocity. Why? Because if I say that I am getting 20 pulses in, let's say, some time, so what is the estimated speed? It is 20 into something which gives you the amount of rotation divided by t, delta t. Okay, so that will give you the velocity. So it is very often used to estimate velocity also. Let's look at a force torque sensor. So this sensor is used to measure the forces and moments which are acting at the end effector or at some other points like the wrist. Okay, so we can either measure these forces and torques at the joint or the wrist. So the force torque joint sensor, you can estimate the torque by strain gauges at the joint itself. Okay, so there's a motor, there's a joint, maybe there's a transmission in between, and I can set up something with a strain gauge which will tell you how much is the torque which this motor is applying by measuring some output from the strain gauge. The force torque wrist sensor is more interesting. It is mounted between the end of the arm and the end effector, and it can measure all 6 components of force and torque using strain gauges. It is extensively used in force control. I would like to control the forces which the end effector is applying to the environment. Okay, and in any control, if you have to measure and use a feedback. So this force torque sensor is used to measure the force, and then this feedback control is used to make sure that the desired force or torque is applied. Okay, the performance specification to ensure that the wrist motion generated by the force torque sensor do not affect the position accuracy of the manipulator. This is very important. So if you are going to mount a force torque sensor at the wrist, it should not affect the kinematics. Okay, it should not say because of the force torque sensor some error in tracking is introduced. Most of the time, such a force torque sensor, which I will show you next, is made from a single metal block to avoid hysteresis. Okay, so how does it look like? So the force torque wrist sensor consists of a block like this. As this white here is connected to the end effector, and the outside here is connected to the body of the robot or to the other part of the robot. So basically, if you, let's say you are taking some tool here, let's say a wrench or a screwdriver, which is connected to this white portion, and some force and moment which are applied on this wrench. Because of these members in which we mount some strain gauges, these columns or these beams will deflect because of the force which is applied at this white region. And by measuring the strains, we can find what is the force and the torque which this end effector is applying to the rest of the robot body. Okay, so let's do it a little bit more detail. So the Z axis is as shown this way. So I can apply a Z force and I can also apply a MZ moment. Likewise, I can have a Fy force and an My moment, and an Mx force, Mx moment, and an Fx force. We have 8 strain gauges. So we have W5, which is on this face, okay, W6, which is on this face, W4 here, W3 here, W2 in this face, W1 in this face, W7 this way, and W8 this way. Okay, so if this bending is about if there is a torque bending which is about this axis, so there is a force acting here and a force acting here. Okay, so the strain gauges W4 and W8 will see large outputs. Okay, because there is no bending on the other face. Likewise, if the Fz is being applied, okay, then you can see that this second strain gauge, okay, and the fourth strain gauge, which is this one, the 8th strain gauge, which is this one, and the 6th strain gauge, which is this one, they will see the Fz force. Okay, and likewise for Fx, Fy, Mx, My, and so on. So I can find a relationship between the 6 components of force and moment, Fx, Fy, Fz, Mx, My, Mz, which is this variable f, and the strain gauge readings, which is there are 8 of them, W1, W2, W3, W4, 5, 6, 7, and 8. Okay, and find the relationship between the strain gauge values and the external force. Okay, so let's just check once. So suppose I am applying Fx, which is in this direction. Okay, so which strain gauge will see the maximum output? It will bend in this direction, right? It will bend like this. So omega is W3 and W7 will see maximum output. The others will see very, very small output, basically due to coupling. So you will have a non-zero elements R13 and a non-zero element R17. Okay. Likewise, all other. So suppose let's see what happens when you have my. So my is a moment about this y-axis. If you have a moment about this y-axis, you can see that this W2 and W6 outputs will be large. So we can fill up this matrix with some variables, and then these quantities can be obtained using calibration. Okay, so you apply a known force Fx and see what are these values. You change this known force Fx and see the value, and then you do some kind of a calibration for each one of these Rijs. So once you have calibrated, then this R matrix is known. Okay, and then if you measure some strain gauge readings, we can multiply the strain gauge readings with the R matrix and obtain the Fx, Fy, Fz, Mx, My, Mz. Okay, so this is the basic idea of a force torque risk sensor. By measuring the strain gauge readings, we can find the external force that the robot is applying. At ISC, we had developed another different kind of force torque sensor. This is based on a Stuart platform. So basically what we have is a Stuart platform, which is the top platform here, and there is a fixed platform. And as I showed you earlier, that there are these legs. So there is a joint here, there is a joint here, and instead of that prismatic joint, which is sliding in and out, sliding joint, we have a ring like this. So think of it that if I apply a force in this direction, this ring will deflect. Okay, from a circular, it will become more oval. Okay, and if you can somehow measure the strains acting at this in this middle layer of this ring, okay, the middle part will see the maximum strains, not here. Okay, in a cantilever beam, if you apply a force at the end of the cantilever, the base of the cantilever sees the largest strain and stress. So the largest strain will be here. So we measure the strain gauges at this location here, and for 6 of these we measure all the strains, and we can relate the force and moment which is applied at the top platform to the strains acting on this rings. Okay, and you can do calibration, and although I'm not discussing here now, this sensor, force torque sensor, is designed such that it is more sensitive to Fx, Fy, and Mz. Okay, we can also design a force torque sensor based on a Stuart platform for some other components of force and moment. In this one, the legs are more or less vertical. Okay, this hexagon at the top and the hexagon at the bottom are exactly equal. With such a design, you can show that Fx, Fy, and Mz will be very, very sensitive. Sometimes that is required. Okay, in many applications, some forces and moments are very small, but you still need to measure them. So it is automatically getting amplified in Fx, Fy, and Mz direction. Okay, so we did this calibration. So we apply some known force. Okay, so we'll plot Fx, Fy, and Fz. So you can see that the Fz is not changing much, whereas Fx and Fy is changing in the in the first leg, and so on. So these plots show that this sensor is sensitive to Fx and Fy components. These are the plots of applied external force and the leg forces that you are measuring. So in each of these 6 legs, we measure the strains, and from that we can calculate the force. We can also obtain plots for Mx, My, Mz when you apply external moments. Okay, so if we apply some external moment on the top platform, we can measure the strains in the legs, and then we can compute the forces which are happening on the leg. And it turns out that Mx and My is not very sensitive, whereas the same is very sensitive for Mz. So when you apply an external moment, Mz readings are very large. Okay, so this is a well designed or a purposefully designed force torque sensor such that we get very high sensitivity in the Fx, Fy, and Mz directions. We have also built force torque sensor where some other directions are more sensitive. Let's continue. Let's look at sensors in robots which are external. Okay, so what is the purpose of external sensors? To detect environment variables for robot guidance, object identification, and material handling. So if I want to see that whether the correct object is there, and then I can command the robot gripper to go and pick it up. If the correct object is not there, if I cannot identify the object, maybe I don't want the robot to go to that place. So there are two main types, contacting and non-contacting sensors. The contacting sensors basically respond to physical contact. Okay, so they are touch sensors, basically some kind of switches and photodiode LED combination. We can also measure slip and we can also measure touch. Okay, basically we can have resistive or capacitive arrays and you can feel the environment. Okay, we can feel whether it is rounded or some other shape. Non-contacting sensors detect variation in optical, acoustic, or electromagnetic radiations or change in position and orientation. Okay, so we can have proximity. There are various kinds of proximity, which are inductive, capacitive, optical, ultrasonic. You have range sensors, which can be capacitive and magnetic. It can be a camera. You can also use sonar. You can use laser rangefinder. You can also use something called structured light. So I will show you a few of them. You can also have color sensors to detect the color of the object. I'm not going to discuss this in detail. And then we can measure speed and motion of the object in the environment. Okay, so there is something called Doppler radar. Then we can have a camera. We can also have accelerometer. We can have gyroscope. Accelerometer and gyroscopes can be used to measure the speed and angular velocity or linear acceleration and angular acceleration of the object. We can also do identification of the object. We can again use a camera. There is something called RFID. Okay, so we can have tags on the object and you can read the tags using this radio frequency ID and figure out whether it is the correct object or not. We can have laser ranging and we have ultrasound. Finally, we have localization. I want to know where my robot is in the workspace or in the environment. So you can either use compass, you can use odometer, you can count, if it is a mobile robot, you can count the rotation of the wheel and figure out how far you have traveled. You can have GPS and you can also use camera. So as you can see, camera is very, very useful. It can be used in many such applications. Quickly go through some of these common sensors. So if you want a touch sensor, so basically what do we have? We have a micro switch and a LED and photodiode. Okay, so this sensors allows you to touch, feel, see and locate the object. So if there is an object in this finger mechanism and if it touches, you will get a signal from these micro switches. You can also see that this light beam will be blocked and you know whether the object is inside the fingers or not. Okay, this is a simple LED photodiode pair used to detect presence, absence of object to be grasped. So I would like to know whether the object is there before I command the robot or the gripper to grasp it. Okay, when do you stop? When the micro switch detects that it has touched. You can also have external sensors which are also to measure slip. So basically it is again like a gripper, but inside the gripper there are like a object here. There is a dimpled ball. Okay, so the actual object is here. And in this dimpled ball, it is connected to a disc which can rotate. So when the ball rotates, this disc below can touch some contact points here. Okay, so if the object is slipping in this direction, then the contacts will be here. Okay, and if it is slipping in some other direction, you will have some other contact. So A slip sensor is basically used to detect if the grasp object is slipping. It's a free moving dimpled ball. It deflects a thin rod on the axis of the conducting disc. Evenly spaced electrical contacts placed under the disc. This is a schematic. It is much more compact. If the object slip past the ball, the moving rod and disc, electrical signals from the contact to detect slip are obtained. Okay, and the direction of slip is determined from the sequence of contacts here. You can also have what are called as tactile arrays. So it's a skin-like membrane to feel the shape of the grasp object. Okay, you can also use to measure force torque required to grasp the object. And basically, as I will show you in the next slide, there is a change in resistance or capacitance when you apply a pressure on an object. Okay, and that change in resistance or capacitance is used to feel the shape of the object. Okay, so typically a tactile sensor consists of a thin rubber skin. There is a set of electrodes which we will call X electrodes, and another set of electrodes which are perpendicular to this called the Y electrodes. So we send current through one set of electrodes and we measure in the other set. So basically what happens is the magnitude of the current is proportional to the change in resistance due to the deformation of this piece of this conducting material. So if there is an object which is sitting here and you are gripping it, some points between the X and Y electrode will be shorter than the other points. So the resistance between, say, this point and this point is different than resistance between this point and some other point below. Okay, so and that is seen by the change in the current when you scan the Y electrodes. The current is going through the X electrode and you scan the Y electrode. So in some places the currents will be smaller. Okay, it also, you can sense the change in capacitance. So if this material changes capacitance when you compress it, we can also use that. So these are sometimes called as artificial skins. Okay, there are also attempts for artificial skins using other physics. So we can have a fluid filled membrane, and when you press, the fluid will change, the shape of the membrane will change, and from that you can find out the shape of the object. You can also have what are called as Hall effect sensors. Okay, and we can have an array of these Hall effect sensors which also tells you where there is contact or where there is pressure. We can also have MEMS sensors. Basically, these are silicon pieces which are micro machined and doped with strain gauge flexure. Okay, so it's like basically lots of strain gauges, and when you use this sensor, it can tell you where the strains are different. And the strains are different wherever there is pressing or wherever there is deformation. Okay, and wherever there is deformation, if you have several such points, you can get an idea of the shape of the object. So these tactile sensors allow you to touch, feel, and sense the shape of the object that you have grasped. You can also have external sensors which detect the proximity. Okay, so it detects basically the presence or absence of an object near to the robot. It is not for large distances. So it works for very short ranges between, let's say, 15 to 20 millimeters. It is frequently used in stationary and mobile robots to avoid obstacles and for safety during operation. Okay, there are four main kinds of proximity sensors. You can have inductive, capacitive, ultrasonic, and optical. So I will show you a few of them, how they work. So the inductive proximity sensor basically consists of a coil and a magnet. So if you bring this object closer to a steel or an iron or a ferromagnetic object, the field lines will change, and you can sense the change of the field lines in this coil. So for example, it could be like this. The coil is seeing nothing, and when you bring something, you can see some intersection of the coil with the field lines. Okay, so the change in flux introduces a current pulse with amplitude and shape proportional to the rate of change in flux. Okay, so we can get an output which looks like this when you bring this magnetic inductive sensor closer to a ferromagnetic object. So if you bring it slowly, the voltages will be lower than if you bring it at high speed. Okay, typical response is that it works only very close by. Okay, so if you have some plot, so if you go far away from the object, the output is very low. So this is very useful where access is a challenge. I cannot go to an object very close to each other. So if I can take this probe and come close to it, I can detect whether there is a metal object there or not. Okay, unfortunately, it is limited to ferromagnetic materials. You can have capacitive proximity sensors. So basically, it consists of a reference electrode and an active electrode. In between, we have air, and then we have sealed, and then we have some circuits inside. So basically, if you bring this electrode, for which there is a voltage which is applied, and you bring it near an object, the equivalent capacitance between this electrode and the outside will change. Okay, so the change in capacitance can be sensed with distance. So if it is like far away, like 15 or 20 millimeters away, then the change in capacitance will be very small. But if you bring this active electrodes very close to an object, the change in capacitance will be much larger. Okay, so it is very similar to this magnetic inductive idea, except it is using electrostatics. It can sense metallic as well as non-metallic objects. Okay. As I said, there is a reference electrode with some voltage. There is an active electrode. There is a electrostatic, so some capacitance is there. When you bring it closer to an object, the capacitance changes and you will get a different voltage. Okay. So as I said, the object's entry in the electrostatic field of electrode changes capacitance. Okay, oscillations will start once the capacitance exceeds a predefined threshold. You can have an RC circuit there. So this triggers output to change between on and off. Okay, so you can sense and you can set the value of this oscillations. If it is below some amount, there is no object. If it is above some amount, it is close to the object. When the object moves away, the oscillator's amplitude decreases, again because change in capacitance is smaller, and then we can change it back to the original state. Okay. If you have large size and dielectric constant of the target, it means larger capacitance and easier detection. Okay, so there is something called dielectric constant which modifies how much the capacitance is changing. If the size of the object is larger, then the change in capacitance is also larger. And it is very useful to detect level through a barrier. Okay, because you can't go to the object because there is a barrier, but you can take this capacitive proximity sensor and find out what is the level or where the object is. We can also have ultrasonic proximity sensors. Basically, these are electroacoustic transducers. We send and receive high frequency sound waves. The emitted sound waves are reflected by an object back to the transducer, which switches to the receiver mode. Okay, the same transducer is used for both receiving and emitting signal. Okay, fast damping of acoustic energy is essential to detect close proximity of objects, and basically achieved by using acoustic absorbers and by decoupling the transducers from its housing. This is typically of very low resolution. We can also have optical proximity sensors. These are called light beam sensors. We have a solid state LED acting as a transmitter by generating a light beam. Okay, a solid state photodiode acts as a receiver. The field of operation of the sensor is this long pencil-like volume formed due to the intersection of cones of light from a source and a detector. Any reflected surface that intersects the volume gets illuminated by the source and is seen by a receiver. Generally, a binary signal is generated when the received light intensity exceeds the threshold value. So we can see whether there is an object in front of you or not. We can also have range sensors. Range sensors are typically used to measure longer distances, not close to the robot, but objects at a much larger distance. We can use electromagnetic or electrostatic or acoustic radiation. Okay, so it looks for changes in the field or the return signal. These are highly reliable with long functional life and no mechanical parts. There are four main types of range sensing which are used in robots. One is called triangulation, one is called structured lighting approach. Then you can sense the difference in the time of sending and receiving the signal. These are called time of flight range finders. And then you can have camera or vision. Okay. The main application of range sensors are in navigation in mobile robots, obstacle avoidance, locating parts, etc. So let's look at triangulation. So basically we have a emitter. Okay. So it is sending out a narrow beam of light. Suppose there is an object and you can scan or rotate this emitter, and there is a detector which is at a distance d. This b is known. So when you are rotating, when this object is directly in front of you, you will get a large signal. Okay. So the detector output is peak when the illuminated patch is in front. So if b and theta are known at that instant, we can get d is b tan theta. Okay. So if you change b and theta, one can get the object, the distance of the object at different points. But it must be visible to this light source. There is almost no computation required. This is very, very simple. All we need to do is know what is B and then find when you get the peak detection and the angle at which the peak detection is happening. And then we quickly know what is D, which is just we need to do tan of that angle. It is very slow because we have to do 1 point at a time. Okay, so as you can see, if you send this beam, most of the time it is scattered. If it were a mirror, this will not work. This idea will not work. So those are called specular reflection. This object or this technique will work if the object is showing Lambertian reflection. Basically, it is scattering. If it was specular, then the I equals R, you will not see anything at the detector. The next well-known way of detecting range or measuring range is something called structured light. So let's look at what it involves. So we have a source of light, but this source of light is now generating a sheet of light, not a single beam. Okay, and let's assume there are these objects in this scene. So how do we generate a sheet of light? We can generate a sheet of light through a cylindrical lens or a narrow slit, okay, like a projector. So when this sheet of light intersects an object, okay, and if you're looking at this scene from a camera at a slight angle, you will see these lines. You will see one line, one more line, then there is a gap, one more line, and there is a curve, and so on. Okay, so the camera, which is offset slightly from the projector, views and analyzes the shape of these lines. Okay, and by using some kind of calibration and by knowing what the shape of the line is, we can find out that this object is nearer than this object, and we can even get a sense of distance by calibration. Okay, so the distortion of the line is related to the distance and can be calculated. The horizontal displacement in the range is proportional to the depth gradient, just to give some more information. And integration gives absolute range, and we need to calibrate to obtain the distance, okay, the range. It is very fast, advantage, very little computation is required, and can scan multiple points or entire views at once. Okay. The big thing is you should be allowed to shine a sheet of light in the scene. Otherwise, this whole thing does not work. The time of flight sensor works basically with the idea that you send a pulsed signal either from a laser or an ultrasonic device. You find the time taken by the pulse to return from a surface from where it is reflecting. Okay, so if d is the target distance, c is the speed of radiation, and t is the elapsed time, then d is ct by 2. Very straightforward. So for light, this is not very useful because c is very large. It's like 3 into 10 to the power 8 meters per second. Okay, but it can be used for measuring large distances, because if it is very close, this elapsed time will be very, very small. Okay, so if you want to, as an example, if you want to measure a range which is plus minus quarter of an inch, we need to measure time intervals of the order of 50 picoseconds, which is not very easy to do. However, this idea can be used for acoustic or ultrasonic radiation. Okay, why? Because this c is very much smaller. It is 330 meters per second as opposed to 3 into 10 to the power 8 meters per second. Okay, this time of flight sensors can only detect distance at one point in its view from wherever the reflection is happening. And if you want to find different distances, okay, we have to scan the object. Another way of using the time of flight is by modulation. Okay, so the idea is the following. Instead of measuring the time of flight, we will measure the phase shift, okay, of the beam. So we have a laser beam, and then at some L from the detector, then we split the beam in two ways. One directly goes to the phase shift detector, and one goes to the object and gets reflected. Okay, so the phase delay between the two beams is measured. So the distance traveled by the first beam is basically L. The distance traveled by the second beam is d prime, which is L plus 2d, and d prime is L plus theta by 360 into lambda, where theta is the phase shift. Okay. So if you can measure the phase shift, so for theta equals 360, the two waveforms are aligned, and d prime is L and d prime is L plus n lambda. Okay, the waveforms cannot be differentiated on phase shift alone. If you restrict theta to less than 360 and 2d to be less than lambda, so then this distance is directly related to the phase shift theta, and in fact the expression is theta by 360 into lambda by 2. So I know the wavelength, I can measure the phase shift, and I can find the distance. Okay, so typically lambda is very small. It is impractical again for robot applications. Okay, so lambda of light is very, very small, is of the order of some microns. But we can modulate this laser light. This is what I meant. Okay, so we can modulate that beam with a waveform of much higher wavelength. So for example, if the modulating frequency is 10 megahertz, then this lambda, which is c by f, is 30 meters. Okay, and distance up to 15 meters can be now measured. Okay. The advantages of this continuous light technique is it yields intensity as well as range information. It requires very little computation, and lasers do not suffer from specular reflection. and it is expensive and not so robust. Okay, it requires much higher power. The range sensors, which are ultrasonic, are very similar to pulsed laser. Instead of a light pulse, we generate an ultrasonic chirp, okay, which is transmitted over a short time period. From the time difference between the transmitted and the reflected wave, D can be obtained, and it is generally used for navigation and obstacle avoidance in robots. Okay, remember the speed is much smaller, so we can find out distances closer. It is much cheaper than a laser rangefinder. Okay, shorter range is more desirable. If you want to measure large distances, these ultrasonic waves will disperse and you will not get a very good signal. Okay, the wavelength of the ultrasonic radiation is much larger. Unfortunately, it is not reflected very well from small objects and corners. So I cannot use this ultrasonic range sensors if the object is very small. The ultrasonic waves are also not reflected very well from plastics and some other materials. So if you have lots of plastic in your environment, and if you have an ultrasonic range sensor, it will give sometimes erroneous results. Finally, we have vision sensor. Okay, as I have mentioned earlier, it is one of the most powerful and complex form of sensing. It is analogous to human eyes. Okay, it comprises of one or more video cameras with integrated signal processing and imaging electronics. It includes interfaces for programming and data output and a variety of measurement and inspection functions. Okay, this technique is also sometimes referred to as machine or computer vision. Okay, there is a whole field called computer vision. There are lots of work and lots of research and lots of papers in this area of machine vision and computer vision. Okay, a large amount of work is done in computer vision simply because the computations required are very large, okay, compared to any other form of sensing. So instead of proximity or laser rangefinder or any of these techniques, cameras require a huge amount of computation. And only very recently we can have processors which can process the measurement by a camera and obtain good estimates of distance. Computer vision can be subdivided into 6 main areas. First is sensing, 2 is pre-processing, third is segmentation. This is an important part in computer vision. This takes quite a bit of time. Okay, I need to know where there is shade and where there is image, okay, where the reflection is. Okay, we need to know the edges. That is what is called segmentation. Then you can find some description, then you need to recognize the object, and then you need to interpret. So each of these requires a huge amount of, or significantly large amount of computing. There are 3 levels of processing. We have low level vision, which are primitive in nature, requires no intelligence on the part of the vision functions. Sensing and pre-processing can be considered as low-level vision functions. Okay, medium-level vision, we extract characteristics and label components in an image resulting from low-level vision. This is the second stage. It requires segmentation, description, and recognition of the individual objects at this stage. Okay, so is it a cube? Is it a sphere? We need to recognize. Okay, so these are some of the medium level vision functions. And the high level vision function is basically we want to emulate cognition. Okay, looking at a scene, once we know it is some object, can we infer something or can we take an action based on that? So that is what is cognition. Okay, there are an increasing number of robotic applications using vision sensors. This is primarily due to the increase in computational capacity and low cost of camera. So there are now cameras which are very cheap, okay, and which can be used for computer vision. The vision system can determine the distance of objects. It can determine the geometrical shape and size of objects. It can also determine color, brightness properties of objects. It can be used for navigation. It can be used to make a map. It can be used to do obstacle avoidance. It can even be done for Cartesian position and velocity feedback. Okay, so if I know the distance, I can somehow obtain the estimate of velocity also. It can be used to locate parts and many other usage. Okay, a vision system can also learn about the environment. There's a lot of research going on to automatically do this medium level segmentation and trying to figure out what object it is. It can also be used to acquire knowledge and intelligence. Okay. Vision systems are extensively used in autonomous navigation in mobile robots. Mars rover is a simple example. The rover is moving around in Mars. There is a time delay between the signal coming from Mars to JPL or wherever it is controlled from. Okay. In between, it must do something autonomously because it can't wait for instructions always from Earth. Okay. So it can. So that is what is called autonomous navigation. So a camera is there which will see whether there is a ditch in front or not while it is moving. If there is a ditch, it can take some decisions and it can stop or it can go around. It is also seen in self-driving cars. Nowadays, there are many self-driving cars which are coming up, and they have vision cameras which can sense whether there is a person in its path or not, or whether there is another car in front or not, or it can even sense whether there is a green light or a red light at a traffic intersection. So the use of vision system is increasing rapidly, and as the technology improves, it is expected to become more and more mature. There will be many more uses of computer vision and vision technology. I'll end this part on sensing with one example of a sensor-based robot, a very well-known example. This is called ASIMO. Okay? ASIMO stands for Advanced Step in Innovative Mobility. So basically, this is a humanoid robot developed by Honda Car Company. It's very far from their normal line of business of making good cars. Okay, so this robot, which is shown here, it looks like a humanoid. It has legs, it has arm, it has a head in which there are lots of sensors. There are sensors for vision, speed, balance, force, angle, and foot area. It has 34 degrees of freedom controlled by servo motors. Okay, there are 34 joints in this robot. Okay, they are all controlled by servo motors. This robot is capable of walking and running. It can maintain posture and balance. It can climb stairs and avoid obstacles. So in this example, you can see that it is trying to play soccer. In this example, it is climbing stairs. Okay, in this example, climbing down, but it can climb up also. It is capable of having some intelligence. Basically, what is the level of intelligence it has? It can chart a shortest route from point A to point B using the camera. It can recognize moving objects and take decisions. It can distinguish sounds and recognize faces and gestures. So if it is talking, it can turn towards you if you are talking, and then it can shake hands. So there are these examples of this robot shaking hands with very distinguished people, okay, on its own. So this is one of the best example of sensor-based robotics. So in summary, the main elements of a robot are links and joints, actuators and transmission, sensors, and computing elements. The robot is a very expensive equipment and sophisticated and with expensive components. Sensors and computing add intelligence to the robot, and more of sensors and computing are being employed in robots. Sensors, computing, and algorithms make up more than 60% of the cost. Okay, so you might think that the motors are very expensive. That's not true. The sensors, computing, and algorithms which go into making a robot intelligent and autonomous are almost 60% or more of the cost. Okay, so with this, I will stop this lecture. We looked at the main elements of a robot. In the next lecture, we'll look at some of the modeling and analysis techniques used in robots.